Hey everyone! In this video we will talk about the method of transformations as a second way to find transformations of random variables. So the method of distribution functions, which we talked about in the previous video, is a pretty general technique that we can use to find the distribution of a transformed random variable. However, we might want a quicker option, and it turns out that if we have what's called a monotone transformation, so either a non-decreasing or a non-increasing function, this is a pretty quick option that we can use. So let's start by defining the method of transformations. We'll let u be h of y, where h of y is a monotone function, either non-increasing or non-decreasing. It can level off at some point. That is legal for these types of transformations, such that the density function f of y is greater than 0. So here's how we'll attack this problem. We'll start by finding the inverse function. So y equals the inverse function of h of u. We'll find the derivative of the inverse function. And then this turns out to be our density of u. So little f of u is little f of y evaluated at the inverse function of u times the absolute value of the derivative. So a pretty quick plug and chug method for finding these transformations. Now, why does this work? So suppose that h of y is an increasing function. Well, then the CDF of u, so the probability that u is less than little u, is the same as the probability that h of y is less than or equal to little u. We'll apply the inverse function h of y on both sides of the inequality to get the following statement. That is the probability that y is less than the inverse function evaluated at u. Okay, so then that is our CDF of u, the inverse, or the CDF of y evaluated at the inverse function. In order to then find the PDF of u, we'll take the derivative. So it's the derivative of the CDF of y evaluated at the inverse function with respect to u. So then by just applying the chain rule, we get that this is the PDF of y evaluated at the inverse function times the derivative of the inverse itself. Now, if we have a decreasing function, then it turns out that the decreasing function itself, or that the inverse function, h inverse, is also a decreasing function. So this changes things just a little bit. So we say that the probability that capital U, or the big U, is less than little u, is the same as the probability that y is greater than or equal to the inverse function. Again, because the inverse function is a decreasing function. So then our PDF is 1 minus the PDF of y evaluated at the inverse function of u. So then we'll use the absolute value to guarantee that we get a valid density function. Because when we take the derivative, we have a negative here. It turns out that this derivative will also be negative because h inverse is a decreasing function. We want this to be a positive. These negatives will cancel out, so we'll just use the absolute value when we write this in our formula. So we're good to go. So as long as we have a monotone function, either non-increasing, non-decreasing, we are good to go, just plugging in. Now let's take a look at some examples from the previous video just to see how much faster this method of transformations truly is. So we have the amount of sugar that's produced that has a density function given by this, 2y, evaluated from 0 to 1, where y can range from 0 to 1, excuse me. So we have a profit variable u is 3y minus 1. That is an increasing function, so we can use the transformation method. So we need the inverse function here first. So if u is equal to 3y minus 1, the inverse function h inverse is u plus 1 over 3. We need the derivative of h inverse, which is simply 1/3. Plugging things in, we'll have our PDF of y evaluated at the inverse function times the derivative. So we have 2 times u plus 1 over 3 times 1/3, or 2/9 times u plus 1. Last thing to do, transform the bounds. Pretty simple. So much, much faster than that method of distribution functions was. Let's take a look at another example. So same density function, let's apply a different transformation. And here we'll use a decreasing function. U is equal to 3 minus 4y. So same PDF, decreasing function. So we'll find the inverse function here. H inverse of u is 3 minus u over 4. The derivative of that inverse function is negative 1/4. So here you see why this absolute value is truly necessary. So we'll take the PDF evaluated at the inverse function times the derivative. We get something that looks a little bit like this. Combining terms together, we get 1/8 times 3 minus u. Last step is to transform the bounds. So here u goes from -1 to 3. Much, much faster than the method of distribution functions. Now, the direct application of this really requires that the function be monotone. If the function's not monotone, we run into some wacky stuff when we're taking the derivative of the inverse function. And that's why we want this monotonicity to apply. If it's not there, we really ought to be using another method. So let's take a look at another example here. So we'll let y be a uniform variable from 0 to 1. I'd like to find the distribution of the negative natural log of y. Now this may seem like a weird transformation to want to take, but it turns out that this is directly related to a result that we'll see in Math Stat 2. So this natural log transformation isn't all that unusual. So here's what this function looks like. We have y on the horizontal axis. Y ranges from 0 to 1. We have u on the vertical axis. The negative natural log looks like this on the range from 0 to 1. So it is a decreasing function, so we can apply the method of transformations here. So we'll need to find our inverse function first. So if u is the negative natural log of y, then y is e raised to the negative u. We'll take the derivative with respect to u to get the derivative of the inverse. That's negative e to the negative u. So then, plugging everything in, we get something that looks like this. Our function, or our PDF, is just 1 because we have a uniform density, times the absolute value of the derivative of the inverse. We'll need to transform the bounds as well. This should look like a distribution that we recognize. This, in fact, is an exponential distribution with mean 1. So that's the method of transformation functions. We have one more method that we'll need to talk about, which is the method of moment-generating functions. Before we do that, we'll actually define moment-generating functions since we skipped over that topic previously. So in the next video, we'll talk about MGFs, or moment-generating functions. I'll see you there.